Are you able to share your screen, sir?
Yeah, madam, sharing. Wait a bit.
Yeah.
No, disabled. Who's disabled participant?
Okay, sir.
No,
Now you check, sir.
yeah, now it's okay. My screen is visible now.
Yes, sir. It's visible, sir.
So once again, thank you everybody. Thank you the participants. Good afternoon to everybody. So already we have discussed about box plot. That is a data exploration and data visualization. But we have discussed one of the box plot. It doesn't mean that that is a unique kind of box plot. The box plot, whatever we have discussed, that is called Turkey box plot, because this box plot was invented by a mathematician who is W Turkey. That's why the name of the box plot is Turkey box plot. Because in that box plot, actually we have calculated IC means different kind of quartile in different kind of ways. But we can use a different kind of mechanism there, different kind of statistics again to set our own box plot. So there are different kind of box plot. If you are interested to work on box plot, then also you can propose some kind of box plot. So today we are going to talk about the next data preparation step, and that is called outlier detection. Here, the outlier detection today. So first of all, we need to understand what is outlier. So see, this is a kind of say, you can say space or input space. We're having different kind of observations here. Some of the observations are like these observations are totally different than others. So whenever we have this kind of observation in our say database, then we can say these are the outliers, because these observations are different than other data patterns or the observations of the data set. So if we have this kind of observations already we talked about, those observations should be removed. So now we have another question here. If such kind of observation is there, then what is the problem? The problem is that it can result in poor fit and lower predictive modeling performance. Means the model what we are going to make, the performance of the model will degrade if we are having so outliers. So it's good whenever we are having outliers, the outliers has to be removed. So whenever the outliers are removed, then it can fit the data properly and enhance the performance of the model. Fine. Now the questions, how we can find those outliers, because we have seen the box plot, we have seen histogram of the scatter plot, right? Using histogram and scatter plot, we can find the outliers or from a data set where the data are represented by one or two dimensions. So if we're having one or two dimensional data, then we can use histogram, scatter plot, or the box plot to remove the outliers. But you try to understand, whenever we are having high dimensional data, then using the simple statistics, we cannot find or we cannot identify the outliers. Then we need to have some sophisticated method for that, or some kind of advanced and machine learning method for detecting the outliers. That's the end here of our today's talk. So we are coming now to the next slide. Here we can see actually there are a number of outlier detection techniques, and based on the learning style, the outlier detection technique can be categorized into three categories, and these are the supervised outlier detection technique, unsupervised outlier detection technique, and semi-supervised outlier detection technique. Now, based on the learning measurement, means which kind of measurement we are going to use to find the outliers, then the whole this outlier detection technique can be categorized into four categories, and these are the categories: statistical based, the distance based, the density based, and the tree based, right? But if we use a statistical base, but there are certain kind of limitations. So here we have a limit, we written the limitations. It works well, means statistical based outlier detection technique works well for a single attribute. So if we have a one-dimensional database, then for that one, a statistical based method works very well. In many cases, the database distribution is not known. So I try to understand when we want to use a statistical based method, then we need to know data distribution. If data distribution is known, only then we can find the outliers properly. But in all cases, in most of the cases, it's not possible to know the data distribution. Again, for multidimensional data, it may be difficult to estimate the true distribution. So in those cases, actually, a statistical based method cannot be used. Even if we can use, the performance may not be better. But you try to understand, in some cases, we have seen that even if these are the limitation, or even though limitations are there, still a statistical based approach can work well in many data sets. Today we're going to see, right? So now coming here we have the most popular and the conventional 4 outlier detection techniques which are used especially for the machine learning. The first one here we have that is called local outlier factors. Using local outlier factors, we can find the outliers. Here especially, this mechanism or this technique uses the concept of nearest neighbor. Based on the concept of the nearest neighbor, it finds the score of each observation of a database. If this score is something greater, or if it is greater than a threshold, then we can say that observation is outlier. So you try to understand, in case of local outlier factor, the score is calculated and that score is based on k nearest neighbor, right? And then we have isolation forest. Using say isolation forest, also we can find out the outliers. This isolation forest is also unsupervised algorithm. So this local outlier factor, this is also unsupervised and density based outlier detection technique. Similarly, isolation forest is also unsupervised outlier detection technique, and that is a tree-based detection technique. Especially in this case, the isolation forest takes or calculates the values of different attributes. If the values of some attributes are something different than others, then we can assume that that attribute is exceptional, or that observation is exceptional. If we have such kind of exceptional observation, then we can treat them as outliers in case of isolation forest. Then again, we have another one, and this is very popular. That's when one class SVM. Especially, this kind of outlier detection technique is used for the imbalanced data. Already we have discussed about the concept of imbalanced database. So if we have an imbalanced database, if we want to find the outliers, then if we use the one class SVM, then it works well. But I try to understand, this one class SVM is not as same as SVM. Is a modified version of support vector machine, and this is unsupervised algorithm. Even though the support vector machine is a supervised learning algorithm, and this is also a density based algorithm, we're going to implement all those things, right? And then we'll see the statistics, how they can perform in different databases, right? And especially this one class SVM can be used for regression problem, and it can also be used for classification problem. After that, we have here is a minimum covariance determinant, especially if we have a data samples or input data. If input variables or input data is having Gaussian distribution, in such a case, we can use a simple statistical method that is called minimum covariance determinant, and then it can work very fine in such a case if the inputs are having a Gaussian distribution. This is a statistical based, and this is also unsupervised outlier detection technique. So we talked about some of the popular methods by which we can find the outliers. And now here in this slide, now these outliers can be categorized into 2 categories. One kind of outlier is called local outliers, and another kind of outlier that is called say global outliers. So if we have a global outliers, then those things can be found using the distance measure. But you try to understand, if you're having say local outliers, then by distance we cannot calculate. So if our objective is to find the local outliers, then we have to find, or we have to follow the density based measure. So see, just This is an example here. So if we talk about these outliers is a global outlier. Why? Because it's an outlier from the perspective of all the data observations, right? From the perspective of this chunk of data observation, it's an outlier because the distance is huge. From the perspective of this data chunk, this is also an outlier. From the perspective of this is also an outlier. So such kind of outlier is called global outliers. But if you try to understand, we can have certain kind of say, local outliers. For example, here we have one of the data, right? So this data, if you see initially, you cannot think that it can be an outlier. But you try to understand due to certain characteristics, even if it's not an outlier from the perspective of this chunk of data, but this one can be outlier from the perspective of this chunk of data. So from the perspective of this chunk of data, we can say it's a outlier. So now these kind of outliers are called local outliers. So if we're having the local outliers, then we need to find it. And if we observe, if we follow the distance, then we cannot find. For those kind of outliers, we have to follow the distance-based technique. So now we're coming to discuss about one of the popular technique that is called local outlier factors. Using the local outlier factors, we can find if there are some say local outliers, then those outliers can be detected using these local outlier factors. So already we talked about in case of local outlier factors, generally we need to consider the k nearest neighbor. Based on the statistics of the k nearest neighbor, we can calculate LOF score, that is called local outlier factor score. And now to calculate LOF, we have certain kind of terms here, certain kind of measures, and we need to understand all the measures carefully. If we cannot understand, then when you solve a problem with example, then we cannot understand properly. That's why to understand this LOF properly, just you see carefully this equation and these definitions, because these definitions are very much crucial to understand how to find the outliers using LOF score. So in this case, we need to find the reachability distance, and then we need to find LOF score for all the instances. For this one, the first term which is required here, that is called kth distance of A. So how we can find the kth distance? What's the definition of the kth distance? The definition of the kth distance is the distance between A and its k nearest neighbor. As we're going to find the kth distance, that's why we have to find the distance between A and its kth nearest neighbor. That distance would be the kth distance of A. So for an example, if we consider this example here, and if our objective is to find the kth distance of A, and where you try to understand the value of k is always tunable parameters, we need to assign the value of A. For an example, in this problem, we are interested when the value of k is 3, right? So now we want to find distance between A and its third nearest neighbor. So we need to find the third nearest neighbor because the value of k is 3 now. So if you see A, the first nearest neighbor is B, and the second nearest neighbor is C, and third nearest neighbor is D. As D and E, because we made here a circle, right? As the distance between A to D and A to E, both are same, they are at equidistant. That's why we can say the third nearest neighbor for A is DE or AE. But if you find the distance is same because this is the radius of a circle only. That's why in this case, if you want to find the distance between A and its third nearest neighbor, then it is represented by DA. That's what we have written here, DA, right? So the first term which is required for LOF score, that is kth distance of A, and we have understood here. I think it is clear to everybody. But if you're having any problem, so again, I can repeat it. Try to understand. If you cannot understand this definition, that's not possible to understand the example. And after kth distance, the next concept or the next definition that would be required, that is called kth distance neighbor of A. Now kth distance neighbor means within the kth distance, how many nearest neighbor of A is there? That one is calculated by this equation, right? And this one is represented by KDNA, means this k distance neighbor of A. And here A bar such that A bar belongs to D. D is a set of k distance nearest neighbor of A. Say for an example, this is the set. And now our objective is to find this set. And the element of this set is A bar. So how we can find A bar? Here we have the equation. See here, if we have a distance and the distance between A and A bar less or equals to distance of KA, this KA. You try to understand this KA means what? That is the kth distance of A. And already in this problem we measured kth distance of A is dA. So the distance, the points whose distance is less than dA, those will come under set D. So initially take B. So this distance, this one, right? Only this one. So this distance is less or equals to this distance, but because this KA is representative of DA. So this distance is less or equals to this distance. That's why B is now included in this set. Similarly, we can find here C. And if you find the distance of A and C, this distance is less than DA. So C again comes under that, right? Similarly, now we can find this D. The distance of DA less or equals to DA, condition is satisfied. That's why D is now included. Similarly, we can find the distance between A and E. Now we find the distance A and E, distance of A and E less or equals to DA. The condition is true. As the condition is true, that's why now E is also included here. So now if you find the set, because we are interested to find the set D. D represents k distance neighbors of A. So now if you see k distance neighbors of A, then we have how many? We have 4 observations. So you try to understand, even if we are finding k nearest neighbor where the value of k is 3, but here we have k nearest neighbor or k distance neighbor, that is 4. Why? Because whenever we are having 2 or more samples at equidistant within this circle, then the number of observations would be more. Fine? Because in this case, we are having a 2 observation at equidistant, and they are D and E. That's why both have come here. Fine? So in that way, we can calculate k distance neighbor of A. So now already we talked about 2 definitions, because we are having a number of definitions here. So one is the k distance of A, then k distance of neighbor of A. But see here, I could understand the first hearing students are here. So you take 1 to 2 minutes and try to understand. If you're having any question, then we can discuss on that. So if these 2 are clear, then we have to find the definition of reach distance, that is called reachability distance. And the reachability distance is represented here as reach dist. So would you like to say anybody? Would you like to say anything? Any questions regarding? Yeah.
Any questions, participants?
No question. So now we have to find the reachability distance, that is represented here as reach dist. So how we can find reachability distance? You try to understand, we have to find the reachability distance for each and every neighbors, right? So in this case, we have a k distance neighbor. So we need to find the reachability distance of all the neighbors. So how we can find? Simply we can find this one for max as a condition, right? Within max, we have a 2 distance here, distance 1 and distance 2. Out of this and this, we have to find the maximum one. So what is the first one? Because now we are interested to find the reachability distance from A to D. We are finding the reachability distance A to D. So how we can find this? Max D. This is kth distance D. That is what? Kth distance D. What is kth distance D? Here I have defined here, where kth distance D is the distance of instance D from its kth nearest neighbor, right? So in this example, we have taken the value of k equals to 3. So if we find the k, the distance of d, then which one will come? You see, from d, try to find out the nearest distance. So this one, then this one is the first nearest neighbor, or this one can be the first nearest neighbor, right? You can take any one of them. So this is first, this is second, and this is third. So if we want to find here the k, the distance of d, as we have taken the value of k equals to 3, that's why it becomes third distance of d. So third distance of d becomes here ds. ds is the third distance of d. So that's what we have given here, ds, comma. Then which one? Distance between, this is distance between a comma d. So already we have calculated the distance between a and d. That's a and d. So here we have two distance, right? ds comma ad. But the reachability between a and b is defined by the maximum. So out of these and these, which one is the maximum? No doubtly, this one is the less, this one is the more than maximum. So that's why the max distance is ad here. In that way, actually, reachability distance should be calculated. Whether three distances are clear or not, 1, 2, 3, because this working principle of this algorithm depends on these three distances or these three definitions. This is the distance, this is the distance, and it's a set. So if it is clear, then coming here to find the average reachability distance of A. Now we have to find the average reachability distance. Here we find the reachability distance, right? The reachability distance between A and D. But now we're going to find the average reachability distance. So whenever we are talking about average reachability distance of A, it means we are trying to find the reachability distances of all the k distance neighbors. So that's why here we have taken 1 by k distance neighbors, summation of k distance neighbor max, because our objective is to find the reachability distance each time. So already this definition is given here. I have given again. It's talking about this one only, simply this one, reachability distance. So here we have a max, k the distance of A's neighbor. How many neighbors here we have for k? Here for A, we are having 4 neighbors, 1, 2, 3, 4. So for all the neighbors, we have to find the kth distance. Means for the first case, the first neighbor would be taken. Then the distance between A comma the first neighbor. Then in the second case, the second neighbor would be taken. The third distance of the second neighbor and the distance between A and the second neighbor. Similarly, as we're having k distance neighbor, the side is 4. That's why we need to do the 4 times 1 by 4, summation of 4, and each time we are going to find the reachability distance. The reachability distance is which one? Out of these and these, the maximum one. Already we have talked about. So in that way, we can calculate the average reachability distance. Once we can calculate average reachability distance, then everything becomes much more easier. So our target is up to here. That's simply, if you can calculate, then there you won't have any problem in calculating LOF score. So here we had an example. Now we are going to see one numerical example, and then we'll calculate the reachability distance and finally LOF score of the problem. So here initially we have 7 points or 7 observations. We try to understand whenever I'm talking about point or observation, one observation or one point represents a pattern or a vector, right? A pattern. So here we have 7 patterns, and these patterns are A, B, C, D, E, F, and G. And our objective is to calculate LOF score of all the points here. But you try to understand, if you calculate LOF score for all the points, then it will take more than 1 hour. So that's why we are here calculating only one LOF score, and that is A. Is LOF score? In same way, we can find the LOF score of all the points. So see here, we are interested from here. So now to compute or to complete the calculation of this computation, we need to have pairwise distances of all the neighbors. So if you see here, because here again we are interested to find the value of k equals to 3. So our objective is to take only 3 nearest neighbors. So if you see this point and if you want to calculate 3 neighbors, then the neighbors would be B, C, and D. Because if you keep this one as a center, and if you make a circle, then the circle will come like that. This, like this, right? Like this. So within the circle means the radius would be, this is the center, and the third distance would be the radius. Then we can make a circle, and within the circle, if within the circle the number of patterns which comes, those becomes the kth distance neighbor of A. So here in this case, the third distance, these are the neighbors. If you want to find the 3 neighbors, then it would be B, C, and D. And now if we calculate, because I have calculated, that's why I'm telling. So here we are finding the distances using Pythagoras distance only. We're not using here Euclidean or any kind of thing, because still Euclidean is not defined. So the Pythagoras is applied here. So now keep in mind, if we want to find the distances between A and B, simply we can find 6 square plus 1 square, right? Pythagoras, 1, 2, 3, 4, 5, 6. That is 6 square plus 1 square. So in that way, we can calculate the distance between A and B. So finally, if you compute, the value becomes 6.08, right? So now, because we are interested to find only the LOF score of A, that's why we are going to find the pairwise distance of all the neighbors only. All the neighbors only. You try to understand, to calculate LOF of 1 point, this kind of exercise we have to do. The exercise, whatever we're going to do, that one is to be done to calculate the LOF score of only 1 point, right? So here we have only considered that we have a 3 nearest neighbor, these, and these. So we found all the pairwise distances here in this table. All the pairwise distances in this table, I try to understand. So here from A to B, A to C, A to D, A to E, A to F, A to B, so A to F. So out of all those things, because we are interested on, say, the value of K equals to 3. So 3 nearest neighbor, and 3 nearest neighbor are colored here as, say, green. So for all 3 nearest neighbor of A are colored as green here, you see. Similarly, from B, it calculates all the pairwise distances from B. These, you see, B to A, B to C, B to D, B to E, B to F. But we are interested on only 3 nearest neighbor. So this green color represents the 3 nearest neighbor of B, right? Similarly, we calculated all the pairwise distances from C to all the observations, CA, CB, CD, CE, and CF. Out of all those, 3 nearest neighbor becomes CB, CD, and CE. Similarly, we calculated all the pairwise distances, that's a DA, DB, DC, DE, DF, DG. And we have taken here only 3 nearest neighbor, and these are the 3 nearest neighbor, right? And the coordinates are here. I have this table, and this table is given here to show the coordinates of all the observations. Here, A, B, C, the coordinate of A's observation. This is coordinates. Observation A is coordinate 7, 6. Similarly, B's is 1, 5 here, right? Similarly, C's is 1, 4. You try to understand 1, 4 means C's is 1, 4 means what? C is here, right? So if this one becomes 0, 0, in coordinate geometry, then this is 1, the value of X is 1, and up to here is how much? 1, 2, 3, and 4. That's why C is represented by 1, 4, right? And A is represented by 7 by 6 in the coordinate geometry. How? Because it is 0, 0, right? So if we map it in XY coordinates, then it becomes what? 1, 2, 3, 4, 5, 6, 7, right? So the value of X is 7 for A. That's why here we have a 7. From here, the value of Y, 1, 2, 3, 4, 5, 6. That's why the value is 6 here, right? So in that way, actually, the coordinates of all the observations are given here. And based on these coordinates, we can find these values. And here we found the Pythagoras distance only. But again, you try to understand whenever you try to find the distance between two things like the B and C, BC. So directly there is 1 unit, right? 1 unit, because we're taking each one as 1. So here we don't need to do any calculation. Directly, we can keep the value as 1. So B to C. That's why the value, which one? B to C, C, B to C. Yeah, B to C, directly this is 1. So whenever it becomes kind of hypotenuse kind of thing, then this value can be found using Pythagoras equation. So in that way, we have calculated all the pairwise distances of all the neighbors, which can be the neighbors of A, because here the value of K is 3. That's why we have taken 3 neighbors, because 3 neighbors are coming under the circle, and we have calculated all the pairwise distances of these 3 nearest neighbors here. See, take 1 minute and try to understand. If you have any question, then again we can talk on that. Everything should be clear and transparent. You can have number of questions, no problem, within the discussion.
Any questions, participants? You can write in your chat box also, or you can directly ask. Students, any questions? So far, what sir has discussed?
Yeah, if there is no question, then we're coming. So now just we have calculated the distances, different distances, right? Now we have to keep all those things in equations. And now if we want to calculate the average reachability distance of A, then how we can calculate? We are coming here, and here the equation becomes 1/3 summation of 3. Try to understand now. In this case, K distance neighbor for A becomes how many? Only 3, right? Don't say hodgepodge like that. Don't misinterpret with this one, because here we made the circle, and within this circle we had 4 observations. That's why I have written here 1/4. But I try to understand now the problem is changed. That here just we made this diagram for the conception, for the concept, because this kind of situation may arise. That's why I discussed here. And now here we have the actual problem. So in this case, if we make the circle with the third distance, which one is the third distance? Among 3, 1, 2, 3, which one is the third? The longest one is the third. So this is the third distance, right? Among 3 nearest neighbor, which one is the longest? This one. That one is called third distance. So third distance is 6,32, and that is AC. So we can have a AC. AC can be a radius. Then we can make a circle. So if we make the circle, then we can see that we are having only 3 nearest neighbor, and they are B, C, and D. That's why here we have 1/3, because already talked about here we have K and D. K and D, K distance neighbors. So in this case, we're having 3. So 1/3, the summation of 3, then max. Max is what? Third distance of A's neighbor. Third, because the value of K is 3. That's why we are interested to calculate third distance of each neighbors, right? Comma, distance of A, comma, the neighbor. So how many neighbors we're having? 3 neighbors. So this kind of thing we have to do 3 times. So we're coming here 1/3 max, third distance of B, because B is one of the neighbor. And then comma, distance between A and the neighbor. Which neighbor? Now we're talking about B. That's why the distance AB, right? So this one is done. So same thing we have to do for 2 more neighbors, and these are max. Third distance of C, because C is the nearest neighbor, comma, dist AC, plus max, third distance of D, because D is the nearest neighbor, and then distance between A and D. So from each pair, our objective is to find the maximum. So now keep the values, because all the values are available here. That's why we made this table, because our objective to take number of distances. So this table, all the distances are available here. So now 1/3 max, 3 times we have done. That's why this 3 is not there, and summation is also not there, right? So now 1/3, the third distance of B. Which one is the third distance of B? You see 1, 2, 3, 3 nearest neighbor. Out of 3 nearest neighbor, which one is the maximum? This one is the maximum. So that's why that is called third distance. You try to understand, if we have a K nearest neighbor, the longest distance is called K distance. Fine. So here we have the nearest neighbor, that is B, and the k nearest neighbor of B is these, and these, the three distances. Out of these three, this one is the longest. That's what that is called third distance of B. So third distance of B is 5, 5, comma 6.08. How did we get this one? Because it's the distance between A and B. So already it is calculated, the distance between A and B, that is 6.08. So here, that's why we have 6.08 here, plus from here third distance of C. So third distance of C is which one? Out of 1, 2, 3, this one is the maximum, 6.32. No, third distance of which one? Third distance of C. Yeah, here C is here, C is here. So we calculated k distance of C, this CB, CD, and CE. Out of these three distances, this one is the third distance because this is the longest distance. So that's why we have kept here 4,2, comma distance between A and C. So already we have calculated A and C, that is 6.32. So 6.32. Similarly, from here, third distance of D. So third distance of D, which one? See the D here. Here we have D. Three nearest neighbor of D. Out of these three, this red one is the third distance, that is 1.4. So we given here 1.4, comma which distance? AD. So already calculated AD. This is 5.8. So we have a 5.8 here. So out of the pairs, we need to take only the maximum. So which one is the maximum from here? That is 6.08 plus here 6.32 plus here 5.8. So now if you do the calculation, very simple calculation, then the value becomes 0.06. This 0.06 is the average reachability distance of A. So till now we got the distance, but you try to understand LOF depends on or based on the density based measure. So here I have written the line, density is the reverse of distance. Therefore, local reachability score, this is the average reachability score of A, right? Now our objective is to find the local reachability score, that is called LRDA. This LRDA is the inverse of average reachability distance. So if the distance is more, then automatically density is less. That's a simple concept. So LRDA equals to 1 by RDA. So now if you calculate, then we'll get local reachability score LRDA of A, that is 1 by 6.06, that is 0.165. So that is the local reachability score of A. Till now, LOF score is not calculated. Just we have calculated local reachability score of A, that is LRD, and here that is 0.165. So after it's clear, any question? Any question from the participant?
Any doubts?
No question. Fine. So now, yeah, anybody? Somebody is trying to say, but you can tell anything, right? I can have a number of mistakes, right? No question. Then see here. So after calculating this local reachability score, now we're coming to calculate LOF. So how we can calculate LOF? Now to calculate LOF, we need to calculate this local reachability score of all the neighbors. Just here we have calculated the local reachability score of A. In the same way, we can calculate the local reachability score of all of the neighbors. So if we talk about a B, then the local reachability score becomes 0.193. Initially, we have to find the average reachability score of B, that is here 5.17, and then we need to find the local reachability score, that is 0.193. Similarly, the local reachability score of C is 0.193. We have to calculate similarly, try to understand. So a lot of calculation is there. So again, we can find the local reachability score of D in the same way, that is 0.193. So got the average reachability score of all the neighbors. So once we calculated the average reachability score of all the neighbors and the point itself, then we can find the LOF score of the point. Now, LOF score of the point equals to 1 by 3. Why 1 by 3? Because how many neighbors we're having? 3 neighbors. So average local reachability distance of the neighbors, and that one is directly I have written. I didn't write the mathematical equation here. Again, we could have written here mathematical equation, but directly I have written the terms so that you can understand very easily. 1 by 3. Then the local reachability score of B, local reachability score of D, local reachability score of C and D by local reachability score of or local reachability distance of A. So all the values are now known. So now if we compute this one, and finally we'll get the value that is 1.17. That is the LOF score of A. Similarly, we need to calculate the LOF score of all the points or all the observation of the data set. Now the question, so we got here the score 1.17. So how we can decide whether this is outliers or not? On an average or generally, if the score is 1 or more than 1, then it is treated as outliers. But again, see, it is not guaranteed. It totally based on, or the domain expert can decide what should be the threshold value. Fine. So here, if we consider the threshold value is 1, then we can say A is the outlier. And for different cases in different applications, the domain expert knows very well. So whenever somebody becomes a data scientist is not a person who knows only the machine learning. Data scientist is a man who knows all the things. He is a manager, he is a domain expert, he is a machine learning scientist. So if we have a data scientist here, then he can decide what can be the value of LO, what can be the value of the threshold, so that we can find whether the observation is outliers or not. But on an average, if it is greater than 1 or 1, then we can say that is an outlier. So according to that definition, now we can say this A is outlier because here the score is 1.17. So in that way, actually, LOF works. That part is your. Any question? Any question? After that, we have isolation forest. Any question here? So this is one of the way by which we can calculate the outliers. Now we have another way. Yeah. We have another way that is called isolation forest. By that also we can do. And this is the unsupervised learning algorithm, and it's a tree-based algorithm by which we can find whether the observation is outliers or not. So generally it is assumed that if something or some observation is outliers, so if we make a tree, then that observations will become sleep node very early than others. Means that observations will be terminated in the tree very early than others. Means the characteristics of that observation is something different than the other observations. So if we make a decision tree, that can be understood by if some pattern terminates earlier than others, then we can say that is exceptional because each characteristic is something different than others. And now this isolation forest can work very well for one-dimensional or multi-dimensional feature or multi-dimensional database. It can be applied especially when you make a tree. This tree is a binary decision trees, and we're going to create two branches or two childs from each of the parent nodes. So how that is created, that's a question now. So we're coming one by one, not discussing too much, but I try to understand when we find a score, because in case of isolation forest, again, for each of the, because if it terminates earlier, it doesn't mean, because we have to calculate something. So for each observations, again here, we are going to calculate a score, and that is called outlier score. And that score is calculated by this equation. That's the equation for that. In this equation, this hx is called the path length of sample x. If our objective, if we are interested to find the score of x, then we have to find the path length of x. And here it is EHX. It means what? This is talking about the average path length of a particular sample. So if by average path length, I'm coming with example, not by words only, right? And then here we have a CN. CN is talking about this is the unsuccessful length of a binary tree. And again, this is average unsuccessful length of a binary tree. So by this, by these two terms, by these two parameters, now we can calculate the score. So it is generally, if the score becomes a zero kind of thing, then the observations is very much normal. So whenever it is going to close to become 1, then we can say the observation is not normal. Generally, whenever the value becomes, here it is written, the threshold can be 0.55 or 0.6, or you can keep it 0.7 also. This is up to you. Generally, it is believed that if the observation is very common, then the value would be 0. And if it is very much outlier, very much exceptional, then it's going to be, the score of the observation is going to be 1, right? This 1. And the score can be calculated like that, right? Now the question how we can calculate. So come here, right? So now here we have, for your convenience to understand better, just we have taken a database, and in this database the data is say one dimensional. But the database can be multidimensional. Try to understand. So we have a one-dimensional database here. So we are having only one attribute. This is A1, like that. So we can have number of attributes here. So what it does actually, it picks randomly. It picks randomly one of the attribute out of n number of attributes. But unfortunately, in this example, we are having only one attribute, A1. So we have to take here only A1. Fine? Not one time, multiple times. I mean, how many forest, how many decision tree, binary decision tree you want to create? That's why it is called isolation forest. But still, I didn't discuss about random forest, right? But we, because we did not reach to that level, then only I'll discuss. So if somebody is having a good idea about random forest, then they can understand better this one. But still, I'm just trying to explain this one with an example so that everybody can understand. So here we have, so arbitrary randomly we have to pick one of the attribute from here. Unfortunately, we are having one. So we have to take this one only. Now we have to see the range of this attribute. So if you see the range of this attribute, how much it is? Maximum is 150. Minimum is how much? 4. So in between 4 and 5, in between 4 and 150, one random number has to be generated. And in this case, in the first case, right, when the first binary decision tree is created, the random number which is generated in between 4 and 150, that is 80.36.
There is a question here.
Yeah.
What is multi-dimensional data in this?
Multi-dimensional data, because the data whichever we talked about, that is called multi-dimensional. Swing. Wait. So this is multi-dimensional, right? This is multi-dimensional because here the one observation A is characterized by how many attributes? 2 attributes, right? These and these. Whenever some vector is represented or some observation is represented by more than one attribute, then we can say that is multi-dimensional data. Especially in case of machine learning, we talk about, we deal with multi-dimensional data. So whenever we have a pattern or we have observation, if the observation is characterized by more than one attributes, then that is multi-dimensional data. Fine? So you try to understand here we have a single dimension, right? And then you try, no label is there because already talk about this is unsupervised learning technique. So that's why we don't have any label. So randomly we have created one number between this and this, that is this. Now left hand side means what? This is lower value. So lower of 80.36, which one value is lower? Looking, this value is lower, right? So now this sample number 5 is coming this side. So as it is coming this side, so it is now terminated. Simply terminated because exact value we can get because this is lower than this. If this is lower than this, now this is terminated, right? This is terminated. Which one is terminated now? 5 is terminated. That's why against 5, the leaf is written 1. Now we have this. How much we have? We have 80,36. This one. Now the nodes which will come right hand side of this, the value should be above 80.36. So which number we can now generate? Because the values which are now apart from this one, all the observations lying in between 80.36 and 150. So now we have to create a random number in between 80.36 and 150. And that random number is 12562. That's the random number. So now looking, which are the observation for which the value is less than 125. So if we're having such kind of observation, then those observations will come on left hand side. So looking which observations we're having. Yes, we are having which observations? We are having, see here, we are having this 121, right? And also we have 122. So we are having two observations here, 122 and 121 and 122. So now what we need to do, we need to create, or the algorithm will create a number in between the lowest value 121 and this one. One random number would be generated now. Now that random number is 123. So this is the random number, and that's the threshold now. So now, if this is the random number, which observations will come on left hand side? Looking, this observation is coming because here the value is 121. So that's why it is labeled as 2. Similarly, 122 also coming here. That's why it is labeled as 2. But in between 125 and 123, there is no pattern. There is no observation. There is no observation. But we made a tree, but we made it red because it's an unsuccessful path. Because no pattern is terminated with this path. That's why that is called unsuccessful path. Because we cannot find any pattern whose value is lying in between 123 and 125. You cannot find it here. So this is unsuccessful. Fine. Now we have to find here one value. So now on the right hand side, we can have the values which are higher than 125. So the values can be up to how much? 150. So now again, we're creating a random number in between 125 and 150. And then a random number is generated. That is 146.32, right? So right hand side we're looking, there is only one pattern, and that is 150. So 50 comes here, 150. So 150 comes here and is labeled as 4. That's why 4 is given here. And now in between 146 and above of 125, any one of the random number, because the point which will come like that in this way, that would be greater than 125 and less than 146. So now we need to create a random number in between this. So the number which is created, that is 133.05. So looking all the patterns, we're looking that we're having a 5 here. We are having this sample, and this sample is having the value 132. So 132 comes here and terminated. So it is labeled as 5. That's why 5 is given here. Fine. So now we have here which one? 133. So now we have to create a random numbers which is in between 133 and 146, because whenever some patterns comes left hand side means its value must be less than 146, and it is on the right hand side of this one, so it should be greater than 133. So we have to create a random number in between 133 and 146. So that is 134. So whenever we create 134, looking that 7, this is 7 number, this pattern 3, 1, this is 135. 135 is terminated with label 7. So 7 is given here, and this one becomes an unsuccessful path. So again, we got one unsuccessful path, and all of the observations are terminated here. So if we see one of the tree, similarly, randomly by taking the attributes each time, it will create randomly number of trees. But unfortunately, we are not having multiple attributes here. We are having only one attribute. Even if we are having only one attribute, then multiple times the attribute is taken, and multiple times this kind of random number is generated, and multiple number of trees are created. That's why it's called isolation forest. It's a kind of forest of trees. Number of trees are created. Number of trees have been grown up here. The tree 1, tree 2, like that, if you want to, because you have to give the parameter. This is a kind of, that is, number of trees is a tunable parameter. So how many trees do you want as a designer? You have to give. So if you want to have 20 trees, then give here 20 trees, right? For the sake of simplicity, just we have created here only 2 trees. So one a binary tree 1, and this is binary decision tree 2. Now we are going to calculate, right? We are going to calculate the score of the first sample here. The first sample here, right? So for the first sample, leaf node is 4 in the first tree. So 4 is here. So if you calculate the path length, how much is the path length here for the first tree? 1, 2, 3. So path length is 3 for 4. And 14 is terminated as 14 in the second tree. So 14 is here. So now we're going to calculate the score for the first observation, so that we're looking the leaf node where it is terminated in each of the trees. In the first tree, it is terminated at 4, and we calculated the depth is, or the length is 3. So 1, 2, 3. Similarly, in the second decision tree, it is here. Means binary decision tree, it is here. So length of the path is how much? 1, 2, 3, 4. So looking that in one tree, the length is 3, and another tree, the length is 4. So now we need to take the average, already talked about. So see here in the next slide we have here, just when we calculate S1 score of this one, 2 to the power minus. So this is the formula, right? This is the formula. So this is the average length. Average length path of x. X is which one now? X is the sample S1. So we have 2 to the power minus 3 plus 4 by 2, because it's average. Two numbers are there. That's why by 2. By average of the unsuccessful path. So see here, in case of this, the unsuccessful path is this. The maximum length path, that we can have a number of unsuccessful path in each tree. So in this tree, we have which one? This path 1, 2, 3. So unsuccessful path length is 3 here. 1, 2, 3, 4. 1, 2, 3, 4, 5 here. So the longest path we have to take from each of the tree. So the longest one is 5. Similarly, again we have to take here the longest one. Which one is the longest one? This one is the longest one. So 1, 2, 3, 4, 5. Here again 5. So the length of the unsuccessful path in tree number 2 is 5. And length of the unsuccessful path in tree number 1 is again 5. So if you find the average, then the average becomes 5. So we kept here 5 here, right? So in that way, if you calculate the value becomes 0.615. In the similar way, we have calculated this score, means the outlier score for all the observations from these two trees. Try to understand whenever the tree number of tree would be changed, then automatically the score would be changed, because already I told you number of trees is a tunable parameter. So now if we calculate all the scores here, so now if you keep the score of above 6.5 or above say 7, then we can say there is only one outlier, and that is this one. Why? Because here the score is 0.812. That's why one anomaly is detected, or one outlier is detected using isolation forest for this data set. That is this, because the score is 0.812. So here we have defined the threshold, that is 7.06. Right? So in that way, in case of isolation forest, we can calculate. So I'm not going to discuss about those things. This is what's the benefit or kind of thing, because I'm going to give you the slide so you can see. So these are the benefits and these are the say disadvantages of isolation forest. Fine. So isolation forest has gone. Now a class imbalance problem. So today I'm not going to talk about the class imbalance problem. Today I'm going to talk about, because already we have talked about the outlier detection technique. So how we can find the outliers in Python. We're going to see, and we're going to apply which data set? Iris data set. Fine. So in Python, looking how we can apply, because already here I have shown you how many popular machine learning outlier detection techniques are there. 4. Wait. Here, this one, local outlier factors, then isolation forest, one class SVM, minimum covariance determinant. So we are going to execute all of them, and we're going to do certain kind of analysis on them. So looking how far can you do today. Thank you, everybody. Any question in the presentation? Because now we're going to on hands-on. Any question? Theoretically, mathematically, any question?
Any questions, participants?
For the students, those who are studying machine learning and AI, so my suggestion is that you be strong in mathematics, right? You are strong, I know, very much strong, but be meticulous. How the equations are being are implemented, which kind of thing is there. See carefully and meticulously. Only then you can understand theoretically the things. So if you know theoretically, only then you
One
can.
question, sir.
Yeah.
One question, sir. Which method is good
We are going to
out
now.
of all this you discussed?
We are going to execute now, right? You can see on that. I'm sure that if somebody is mature here, MTech or PhD student, so the analysis which we are going to show now.
Sorry, there was a disturbance, sir. Unmute yourself, sir.
Based on certain parameters, based on certain statistics, you have to analyze and you have to conclude for which kind of data set, which one is better. Because we can have a different kind of data set. The size of the some data set can be smaller. The size of the some data set can be, say, larger. So we have to analyze for which kind of technique is good for which kind of data set. Number one, that if you find the variance of the attributes, variance or number of attributes in the data set, because we're talking about the multidimensional data, if the number of inputs in the problem is larger, then which kind of technique is working good? That can be another kind of analysis. So experimentally, I can show you, but you try to understand. If you understand mathematical and conceptually, then you have to know all the mathematics about all the models. Otherwise, you cannot tell. Otherwise, whichever I'm telling or whichever you tell, that one will be only vague, nothing else. But different
Sir,
kind of.
one more question, sir.
Yeah.
From Nishant, that in which scenario these methods are used? Like there is a particular case in which we need to use a particular outlier detection. That means the student is asking about different applications or examples.
No, you cannot say. You try to understand, because there are different kind of techniques. You cannot say which one is the good and which one is the best for which one. So especially you have to apply on an average all those things, because just I'm going to show you in the same data set, right? You can get different results using the different kind of algorithms, right? Different kind of algorithms. So especially already I have written here some special characteristics are there, and all the characteristics are written here. If attribute values are different, if the attribute values are very much different, right? Because one sample is characterized by attributes, and now the attributes are characterized by different attribute values. Now the attribute values, if the attribute values are very much different, then in such a scenario, you can apply isolation forest. That's why data visualization and data exploration is very much important to select the model. If you're having multiple options, then which options would be good? You have to do data exploration and data visualization. So if you have a data sets where the attribute values are very much different, then in such a case, isolation forest can be used. And see here, if we have the input data looking that the input data are distributed in, say, Gaussian distribution, then you need to use this technique, right? This technique. Fine. So now we are going to see the experimentation, then we can say different outputs we'll get from the same data set. So then you can have a bit or whichever questions you're having, you try to do a kind of research on that. Fine. So today we are here. Initial just isolation forest we are checking. I'll explain all the things one by one. I'll explain all the things. So here, see, this C1 is not going to use because that the functions which under this module, that function is not used here. That's why. So up to here, you know very well, up to here, just I'm cutting up to here, see, up to here, just cut. So up to here, you are well versed till now. What I'm doing here, just I'm importing the file that is iris1 CSV file to a variable that is f1, running this one. So this is f1. So here it will take time initially, the first execution. Yeah, this is the data set, iris data set. And now just putting V here. So already we talked about isolation forest is unsupervised learning technique. So if it is unsupervised learning technique, then we need to use only the independent parameters, means only the attributes. Level 1, because this is a problem, try to understand here, it's a classification problem. These are the inputs, means attributes, sepal length, sepal width, petal length, petal width. And based on that, the output is the classification. But here, as already talked about, that isolation forest is unsupervised learning. So this part is not required. This part is not required, right? This part is not required. So we need to have only this part. So initially the data set is broken. So data set is broken here. The data set is broken here. Just again, I'm cutting from here, cutting out is cut out from here. So now data set is broken because F1 is the data set, and this data set is having this kind of, say, columns. Column. How many columns? 1, 2, 3, 4, 5. How many rows? 150. Out of 150, so we are going to take all 150 in unsupervised learning, but this part we are cutting. Which part? This part. So if we'll cut this part, then how we can cut this part? This is, see here, the F1 is the file, comma, iloc, index location. Here we have a colon, then comma. Already talked about if I have a comma, then it represents what? It represents all the rows. It represents the rows. And we did not mention anything here, right? So no initial, no stop. It means what? We are talking about all the rows. So we are taking all the rows. And from the field of columns, how many we are taking? We are here. We are interested to check from the first to this one. So this one is represented by 0. Already I told you because it starts from 0. This is 0, 1, 2, 3. And we have written here 4 because whenever we have iLog, the maximum is shown this limit minus 1. So the number of columns what we can get, that is 0 to 3. And from 0 to 3, we have to notate this one as this only, then we'll get from 0 to 3rd. So for that one, we have written this code here. Clear? And this part is kept here because I had an initial code, that's why I kept here. Even if this is not required, still this is not required here, but I kept here. So just so that you can understand better. So if you are interested to take this one only in a variable, then how we can slice? Because we are slicing. Slicing means what? A part of the file we are cutting down. That's called slicing. So for the slicing, this iloc operation, iloc function is very good. So we have Y train, and Y train we are going to keep this one, that is F1. So from whole file dot iloc, which one? All the rows. And here we don't have any interval, just we have kept here the 4th one. Means all the rows, but here the column is on the 4th one. So the fourth one is which one? It starts from 0. Already we'll talk about the 0, 1, 2, 3, and 4. So this is fourth one. So now just run this one here. So if you run here, see this one. Still you cannot see. These are stored here. These are stored here. If you are interested to see the value, simply copy, simply paste here. Then you can see here the value. Here, see, already talked about this one. Here we have all the inputs, all the inputs, all the inputs, all the inputs. So see here, we have all the inputs only, right? Class level is discarded from here. Again, if you want to see the class level, which is stored in white train, then you can see very easily. Simply see here. Simply you can see there is class level. This is the class level. Fine. So after that, now discarded, we have discarded. So somehow the operation has to be applied and the score has to be found here. And for that one, what we need to do? See here. Functions are available, right? We don't need to do anything. Just we need to put only there. Nothing else. Nothing else. Just we want to put there only. Very simple. But you have to have a basic concept, right? I'll give you the codes, but you don't try to use my code. If you use, then you can do only this kind of thing. So try to do yourself. When you can do yourself 1 or 2 programs, then automatically your confidence will improve. You must have a different kind, you will have a different kind of confidence then. So paste here. So I'm printing the step. Here step means what? How many columns are there? How many rows are there? For that one actually. The cutting again. So I'm just running this one. If I run here, then I can see the step here. Step means by step we can see how many rows and how many columns are there. So here print x train dot step. So here in this case, in x train, we're having how many? 150 rows. And how many columns? 4 columns. That's why here 4. And here y train step, how many? Only 1, right? We have how many, 1 column, and then how many rows? 150 rows. So only 150 rows. And 1 column means it's not written here. So then, and thereafter just putting here the next one, showing one by one. So now somehow we have to train. Now which one we have to train? This is isolation forest. So putting up to here, cutting down up to here. So now simply you see that we need to have a submodule for isolation forest, and the submodule is given here, right? And this submodule is available in a package. The package name is a scalar ensemble. Because already I talked about this is a kind of random forest kind of thing, isolation forest. So isolation forest is a kind of ensembling method because we have created number of trees there. So all such kind of submodules are stored in this package that is called scalar.ensemble. So from this package, this submodule is installed. In this submodule, the definition, the code of the isolation forest is already defined. Simple thing. So now how we can call using the program this submodule? Simply we can write this one and it's a function and we can pass a number of parameters here. So initially, so next day and thereafter I will pass number of parameters here. But initially, because now we are beginner, so that's why I'm passing here only 1 parameter. That is called contamination. Already we know contamination means what? Which kind of, but how many percent of data we are going to consider as outliers. So that is the contamination. The contamination equals to 0.8. In this what? 10% data is going to be as or going to be treated as outliers. It is trained, it is called, and trained. It is already available. And that one is assigned to ISO. It's a variable, nothing else. It's a variable in the ISO. You can keep any name here. Now we are going to train the model using this function, this isolation forest, because this isolation forest with this parameter is now available in ISO. So that's why we have written here ISO dot fit predict. Now we predict, now we calculate. What calculate? Calculate the isolation score. From where? Or outlier score. From where? From this data. Simply we have given the data here. So see here, this data means we have given the input data. Label is not there. Only the attributes are there. It's trained. Already we have seen. So now using this function, it is now calculating the score. And you try to understand, it calculates the score automatically. And if it finds that it's an outlier, because here somehow the observations whose score is more up to 15 patterns, because total number of pattern in the data set is 150. and we are interested to make contaminant how many? 10%, 0.1. So somehow it will create or it will treat 15 observation as outliers. So try to understand by this function actually, whenever some pattern is treated as outliers, its score is -1. If it is a normal pattern, then its score is 1. Okay. So now for 150 patterns, it calculates already this function, already calculated the scores. If they are the normal, then 1. If they are the outliers, then that is -1. And that is stored where? That is stored in here. This is a variable. You can keep any number, right? Yet variable. Now, just to show you what things are available in yet variable, we have written here printf yet. See here, we're running this one. You can see all ones, +1 and -1. Wait, where? This is. So 1, 1 means the first observation is common observation, normal observation. Second is normal observation. Third is normal observation. These are the normal observation. This one is outliers. This one is outliers. This one is outliers, right? But somehow we have to do in the program so that automatically we can discard all the outliers. That's the objective. So how I have done here, I have write all the codes explicitly. Try to understand. You can use some C-bond kind of thing, and you can put some functions that you can delete very easily, right? But I didn't do, because my objective is not to execute only. My objective is to make you understand. That's why I have written the code in that way. So already have this one, right? So this one is what? Because you know basic Python is a list. It's a list. It's a list. The value which are available in yet now, that's a list. So now what I want to do actually, I want to create one more column in the data set so that I can find out the index of the data set where the value of this one, I'm going to assign some new value here, that is -1. That's my objective actually. That's why I made this one as a data frame. Now this is a list, because whenever I want to concatenate two things together, so both have to be say data frame. If they are not data frame, then I cannot concatenate, right? So I made it a data frame like that. So this is, as you see here, simple. In that way, actually, data frame can be created. So I'm cutting from here, So now all the values yet here. So you know, if you have a list, in that way, data frame would be created. That's from the basic Python. You are experienced in the basic Python. I know. The data PD dot data frame, and this value is assigned to a data frame whose name is anomaly now, right? So now, and this one is assigned, this anomaly column is assigned to a variable that is data. So that's why I've written a data dot a head 20. So up to 20 we can see here. So the value here, right now, it become a data frame by this code. And this data frame is stored now here. So looking how, see here, so data frame. Now we have a data frame here, right? So we just give here the code here. This is data dot head 20, so that we are looking top 20 entries here, the rows here, right? Now what's our objective? Our objective is to concatenate. Which one? With F. Looking with F1. My objective is to concatenate. So how I have done here, see that I have done very simply here, the pd dot concat. By concat, this function we can concatenate two things, two data frames together. So what we want? We want the concatenations row-wise, row by row, or column-wise concatenation. That is decided by x is equals to 1. Already I told you, whenever x is equals to 1, it refers the column operation. Whenever x is equals to becomes 0, then it becomes row operation. So now we want to concatenate F1 and data column-wise. So already in F1, I have 1, 2, 3. Class level is also there, right? No problem. Because now the training is done now. This part isolation forest kind of thing is done now. Fine. Now the objective is the wherever I got -1, wherever I got the anomaly, somehow that anomaly has to be removed from the database. That's my objective. So now this F1, just I concatenate this data, right? And that one is stored in F2. That one is stored in F2, and here I have a print F2. So see here, print F2. So cutting from here, cut out. So see now, print F2 running now. So see you F2, this is the value of F2. This is how many? 1, 2, 3, 4 here class, and here we have anomaly. So one more is here. Anomaly, why we have anomaly added here? Because already we know query on say columns, query on say file. So based on the query, wherever the values of anomaly becomes equals to -1, that index can be identified. So simply we have a code here. Please see here. Simply we have a code here. Please note of. I cannot give yeah. So mute somebody. Someone please. You are creating sound. Mute it. Somebody is creating noise, madam.
You unmute yourself, sir. I am muted all. Just unmute yourself. Yeah.
Okay, fine. So we concatenate, and this is here already we have seen. Now, what's our objective? Our objective from this F2. F2 is the new data set now. This F2. From this F2, we need to identify the indexes where the values of anomaly equals to -1. Already we are experienced because in the box plot we have done this thing. This F2, and then we had a different values, right? So F2 anomaly equals to -1 dot index means wherever the value of anomaly becomes -1, that index is now stored here, index names, and we are printing the index names here. So simply if I execute, then we can understand for which index the value of anomaly equals to -1 means the patterns which are associated with those index, these are the outliers. That's objective. Simply, so we found the indexes here. We have the indexes here. The 13th number observation is outlier. 14th number observation outlier. 15th number observation outlier. 32nd number, 32nd is outlier. Like that, these are the index number of the observations which are treated as outlier using isolation forest. So now what's our objective? Our objective is to somehow, which one? We need to remove those things, drop those things, right? Simply we can drop. Simply we can drop here. We can drop here simply. So F1 dot drop the index names. Which one we're going to drop now? Index names. Already have seen the index name. We're having the indices or indexes where the value of anomaly equals to -1 means these are the outliers. And then I have written comma in place equals to true. It means whatever change is done here, that change should be reflected to F1. That's why I have written in place equals to true. If I don't write here in place equals to true, then changes would be there, but that change will not reflect in F1. But we're coming to that one also. So I'm running this one, fine. So it is expected that in F1 now we are having the data set out of outliers. So the number of data in F1 should be 135 because already we have calculated the number of outliers is 15 and 15 are discarded. And that thing is reflected now in F1 and already F1 is printed out here. So looking how many instances are in F1. Yes, fortunately we're having 135. So 15 are discarded. So if we discard this one, then what happens? You see here that I'll tell you, if we discard this one, then things will change, but that one will not reflect in F1. See here now, printing F1, right? The things will not reflect here. See the size of F1, 150. So we can do this one simply. If we don't write, then the things whichever changes is done here, that one should be stored somewhere else. That is the F2. And now we are printing here F2. So that one can be done. See simply run. So here, see here, if the value is 135, so whichever you want to do, you do like that, because in my subsequent code, I have given F1. That's why I want to change this one and to change this one as F1. Right? So now we have F1, the refined data set after removing all the outliers. Now, if outliers are removed, so here we have done the code. So the final code is running here so that you won't have any confusion. This code here, finally running here, running the code here. Speed, we have this one, right? And all the things are now reflected in F1, 135. So already we know the accuracy of this one without outlier detection, because we have the accuracy of this rich database, iris database. Already we have seen it is around 95 point something. With the same training, same split we are doing now after outlier removal. What is the output we are going to see now? So import pandas, looking from here to here. So we have the same setup. I didn't change anything here. Whenever setup we change, then automatically, because number of tunable parameters are there generally. Yeah? So I didn't change any kind of parameter here. Just I kept here 0.3% as testing and 70% as a training. And F1 as I kept is F1 because I used in this code F1. That's why I made it only F1, right? So see now the code, if you run and then try to understand here, the contamination rate is how much? That is 0.1, means 10% samples are treated as outliers. It totally depends on the designer. You can decide it. So now we're looking how many are there, right? So we have done, and all the reflections are now available in F1, and this F1 is available in this decision tree model. So looking how much accuracy we're getting from here is 92. So if you don't do the outlier detections, if you keep all 150 observations, and if we have the same kind of setup, then the accuracy was how much? 95. But here the accuracy becomes 0.92. Why? Because we have discarded how many? We have discarded here 10%. 10% means we have treated 15 observations as outliers. But the 15 observation may not be outliers. And one thing we know in machine learning, whenever, already I told you, machine learning is what? It's learning from the past data or the historical information. So if you have a huge amount of historical information, then the generalization capability is much more better. Then the modeling, the performance of the model becomes better. So in this case, actually, in this data set, we don't have this much of outliers. We have a data. Some outliers can be there, but 15 outliers are not there. So as we don't have a 15 outliers, but we have discarded 15 outliers, that's why some information from the data set is lost. That's why the performance is dropped. So now we are changing this one, because already you have seen in a box plot, right? By observing one of the attributes, that in 4 cases, there is a bit of miscalculation. There is a bit of mismatches. So if we consider that one in our mind, so now if we want to have 5 or 4 outliers using, say, this isolation forest, so this one can be determined by contamination rate. It can be 4 or 5 if we give 0.3, means this is 3%. So now 3% of the patterns is going to be treated as outliers, right? So it will remove how many? 4 or 5. Looking how many? 5 possibly running. Running will take time. Fine. Looking how many? Finally, we have 145. Means 5 patterns are treated, and these patterns, which are the patterns? 41, 109, 117, 118, 131. These patterns are different in the box plot. You can see the index number in the box plot. These were the different, because there the outliers were detected based on only 1 parameter. Even if here we are going to calculate only 5, but those 5 outliers are calculated based on all the attributes. It's more generalized. So that's why the index will be different now. But now we're going to check whether performance is increasing or not. Again, I'm telling you, it totally depends on the data set. again, many things I'll tell you, many things actually. So whenever you are having a presentation for the PhD student or for MTech or for BTech or somewhere, some conferences, many judges ask, if your performance is only 80% or 70%, then how can you judge your model? Sir, the performance doesn't depend on the model only. It depends on the data set. If the nature of the data set is highly nonlinear, then using any kind of machine learning algorithm, it cannot give more than 60 or 70. So that's the challenge of the machine learning community. It depends, mainly depends on the nature of the data set. If the data set is very much linear, you can use any model, machine learning model or simple model, then you'll get 100% result. So by result, you cannot analyze. If you want to analyze, then different kind of classifier have to be applied to the same setup, to the same data set. And the setup would be the same, right? Many tunable parameters are there in a model actually. So all the tunable parameters you have to keep the same. Then only you can analyze in the database, right? So now looking how much is changing here. Just we just discarded here only 5, and now looking the accuracy, right? Using the isolation first. How much is the accuracy? Yeah, they're 100%. 1, 0. They're in 100%. 1.0 means this is 100%, right? So whenever you change the rate here, again the accuracy will change here. Where we had where this is 1, this is 1 here. So change here 4%. Looking how much is that? So if it is 4%, then how many discarded? 6. And now looking how much is the accuracy? So it's 93%. Accuracy is dropped now, 0.9318 kind of thing. So how many percent? You try to understand the crucial role that means it plays, means this contamination rate plays a crucial role, that how much you are going to get the accuracy from your internet connection. So how much accuracy you're going to get from the classifier, it mostly depends on the contamination rate. So now the question, how much should be the contamination rate? I don't know how much should be. For that one, you have to know some of the tools that is out of the scope of this workshop, because the data visualizations we have used scattered up to scatter plot, right? And then which one? Scatter plot, then histogram kind of thing. So histogram analyze 1 dimensions, scatter plot 2 dimensions. Especially for the data visualizations for the big data, there are certain algorithms. If you run those algorithms, then you can understand how many behavior of how many patterns are different. Then based on that, you can set this contamination rate, right? If any big data is not for this workshop, but I'm telling you, I told you. So there are some tools, visualization tools, because these visualization tools, the conventional visualization tools cannot be applied in the big data. That's why big data becomes a different subject. So thank you, everybody. Possibly you have understood the points. Okay. Thank you.
Thank you so much, sir.
Madam, today I'm just giving you the code and say data set, because in presentation, again, I have to do one thing. So my director is calling me. Wait, madam. I'm just thank you, everybody. Thank you.
Thank you so much, sir. I'll talk to you, sir.